Hello, and welcome to my EC500 final project video. I'm Shane McCormack, and my partner is Everett Carson. Today, I'll be walking through a microfluidic design, mapping, and visualization tool. Widespread use of microfluidics could potentially catalyze great advancements in the automation and efficiency of simple lab processes. However, as of now, microfluidics are generally avoided due to their complicated design process and steep build cost. Our project has the primary goal of easing this design process for the end user. We do this by automating the intermediate design steps, which reduces the knowledge and labor required for labs delving into the creation of microfluidics. Specifically, we take in a design idea in an easy-to-make format and output a Fluigi compatible design. After the design is through Fluigi, the microfluidic device can then be built using the low-cost 3D printer-based Microfluidics. Our project fits into the beginning of this overall flow, and the whole flow's goal is to ease microfluidic design difficulty and lower build costs. Of course, as I mentioned earlier, our project is more concerned with easing the design difficulty of designing a microfluidic device. Now that we've defined the goals of our project, let's explain our tool's inputs. Shown here are the two files the user gives our tool. On the left, the Verilog file describing the microfluidic design. On the right, the user constraint file, which explains the details of each unique microfluidic component used in the design. Let's first take a look at the Verilog file. As you can see, this is a simple module block filled with design statements. This particular file, which we'll use when running our project in a second, describes a system with three inputs, two of these being added together, then that result being added together with a third input, and this going into the final output. Now, let's look at the UCF file on the right. This is where the addition symbol is described as a microfluidic part. The information the user must supply regarding their parts are the number of inputs, the number of outputs, the custom image used for visualizing the component, and the mint syntax associated with it. Currently, this contains a description for a 2-in, 1-out Y mixer. In a more complex design, multiple operators will be defined here. For now, this user constraint file is implemented in a custom format. In the future, we'll move towards a more standardized format, like a JSON list of objects, with an object for each component type. Using this input method is beneficial to the user in that they will not have to instantiate their components each time they appear in their design. The UCF file can be treated as a library of sorts, in which, once a component is defined, the lab will never have to define it again. It is also beneficial that, other than for the one-time device instantiation, the user will never have to write mint code. We've covered the basics and the input for our project. Let's see it in action. As of yet, we don't have a GUI implemented for our tool, so I'm just going to run it from our IDE. So first, our project will need to know where the input files are. And then it'll ask you for what you want your mint output file to be named. Our tool is now output two things: the visualization of our design and the mint file to be used as an input to Fluigi, given that the user would like to continue with building this design. As you can see, our visualization has recreated the design we made in our Verilog file perfectly. However, unfortunately, the custom images where the microfluidic components should be are not currently working. However, if they were to be functional, this is what they'd look like in a similar design. The only difference in this design is instead of two Y mixers, we'd have one Y mixer and one serpentine mixer. which could be easily implemented via our UCF file. As the second output of our tool, we have the mint file that was generated of our design. So you can see that all of our inputs from our Verilog file have been turned into ports in this mint file. All of the microfluidic components we defined and used in our Verilog file and UCF files are here in their proper mint syntax. And then all the connections between the ports and the operators are denoted by these channels. Currently, they're set to default be oriented from left to right, with inputs on the left and outputs on the right. As of yet, we only have the flow layer implemented. However, the control layer could be implemented by taking the UCF and putting another variable in which notes whether the component is a control layer component or a flow layer component. So now we understand the goals of the project, what we inputted, what exactly the project does, and what comes out of it. But how is it doing this work exactly? Briefly, this flowchart describes the project's workflow. Boxed in red is exactly what we did for the project. So, the Verilog file written by the user comes in, gets run through a netlist creator called NetSynth, and then we take NetSynth results and create our custom graph from it. This graph and then the UCF file that the user inputs go into our error checking, which makes sure that every operator from the Verilog file is defined in the UCF, the number of inputs and outputs match up from the Verilog file with how they're defined in the UCF, etc. From there, we translate our graph into a JGraphX object, which then gets visualized. Also, after error checking, the UCF file and our graph are taken in to create a Fluigi compatible input written in Mint. As color-coded, the division of work was as follows. I converted the netlist into our graph and created the UCF parameters. Everett handled error checking, translated my graph into a JGraphX object, and created the visual that stemmed from it. I handled taking my graph in the UCF and turning it into a Mint file. Though not displayed here, Everett handled code submission, and I handled the video. So very briefly, let's go over some code. First, we have our main file, but I won't stay here long, as we just kind of described it in the flowchart. The first thing we do is parse our UCF file. To do this, we leverage regular expressions. Next, we call NetSynth with our Verilog file. We take the results from NetSynth and parse them, creating our own objects for gates and wires, and make our own graph object out of it. Then we take our results from the UCF parsing and the NetSynth results parsing, which is our graph, and we translate it into a JGraphX object. The first thing we do when making this JGraphX is check for errors. And this is, as I said earlier, just making sure that the number of inputs and outputs are correct and that all our operators are the same in our UCF as they are in our Verilog file. Generating this JGraphX object consists of making vertexes and edges. We then visualize our JGraphX object via extending a Java applet. Finally, we take our graph, which is full of objects filled in by the results of parsing our NetSynth results and our UCF results, and we create a Mint file with them. Thank you for watching my presentation on my Microfluidic Mapper and Visualizer tool. I hope you enjoyed it.